Going and let's get started. Good morning. Everybody's ready to ace the exam. But we spend this class period going back and reviewing homework questions and see what we can do to get ready. So, who wants to start? Who has the first problem they want to ask questions about? Want to look at? What you got? 37. Dimensions. Unit analysis. Okay, let's write what we've got here. We're given an equation for v, or velocity, is equal to a times t cubed minus b times t, where t is time. Now what they're asking for are the dimensions of A and B and the SI units of A and B. Well, what's the very first thing we should know? Anybody? We know that if this and this are added together, or subtracted in this case, because subtraction is just the addition of a negative. Ash, behind you. In order to add these numbers together, they have to have the same units, the same dimensions. And we know that if this is equal to this, it too must have the same dimensions and the same units. Well, we know the dimensions for velocity are what? Length divided by time. Distance per unit time. But what are the SI units of velocity? Meters per second. Cyrus, have you turned in your lab yet?
Yeah.
Okay. Sorry about that. We'll get you fixed up. We'll get you taken care of. Now, we know that the velocity is meters per second, which means this must end up being meters per second, and this must end up being meters per second. So, let's start with A. We know that if we multiply it by time cubed, that it's going to become meters per second. Well, what would you have to multiply by times cubed by cubic seconds in order to end up with meters per second? See if we can do this algebraically. Meters per second equals A times seconds cubed So if we divide both sides by seconds cubed, we end up with meters per seconds to the fourth. Let's plug that in. Let's assume A has units of meters per seconds to the fourth. Multiply that times seconds cubed. And what do we end up with? Seconds cubed cancels out 3 of the s's in the bottom, and we end up with meters per second. Okay? So that tells us the SI units of A must be meters per seconds to the fourth. So what would that make the dimensions? Length divided by time to the fourth. Okay, now let's look at B. We know that we multiply B times time, so we have some dimensions that when we multiply by dimensions of time, they become, no, not the definition. Length divided by time. Well, if we divide both sides by one dimension, by one time dimension, then we end up with our unknown dimensions equal to length divided by time squared. So we write the dimensions of B have to be length per time squared. And in SI units, that would be what? Somebody, anybody? What's the SI unit for length? SI units, System International. Everybody remember that one? MKS, meters, kilograms, seconds. So what are the SI units for length? Meters. And what are the SI units for time? Seconds. So it's time squared, so it would be meters per second squared. Now, does everyone see how we got this? No? Okay, let's try it. Well, I don't know. We can repeat it. What is causing us confusion? Go ahead. What don't we understand yet? Oh, it's problem number 37 on page 19, where they give us an equation for speed or velocity, or not velocity, but the magnitude of a velocity. Remember, in dimensional analysis, you're not dealing necessarily, you don't have to write everything in terms of SI units or MKS. That's the one where you put the uppercase letters inside square brackets to show this is the dimension of what you're looking at. velocity would be length per time. Weight or force would be I'll use an uppercase K. You could write an uppercase M for mass. Force would be mass, length, divided by time squared. Or in SI units, what would that be in SI units? Kilograms, meters per second squared, or exactly. What if we were talking about the acceleration due to the Earth's gravity? What are the dimensions? What are the units of acceleration due to gravity? Force is mass times acceleration. The acceleration due to gravity is a specific case of acceleration. Let's just change that to a generic, not necessarily gravity, but any generic acceleration. What would the dimensions be? If it's mass times acceleration, wipe out the dimension of mass, and what are you left with? Length over time squared. Or in SI units, meters per second squared. Go ahead. Mm-hmm. That's the definition of speed is, yeah, we start, well, let's start this over and do it one step at a time. We know the definition of speed is distance per unit time. How far you go and how long it takes. So, we start off with the dimensions of velocity have to be length per unit time. Or in SI units, meters per second. That's how speed or velocity is defined. So that's our starting point. That much we know. We also know that since this is in units of meters per second, we know that this must be units of meters per second, and this must be units of meters per second. Because in order for this to equal this, both of these combined have to have the same units as this. And since they have to have the same units combined, they have to have the same units individually because you're adding them together. You can't add meters per second plus kilograms. That would be physically meaningless. Okay? If you're adding the two numbers, they have to have the same units. And if you're working out a problem and you go to add two numbers and you notice that they don't have the same units, that's where you need to stop and figure out where you went wrong. Because in order to add them together meaningfully, they have to have the same units. Now, meters and seconds are the SI units of length and time. So, and they're asking for two different things. They're asking first for the dimensions of A and B, and then for the SI units of A and B. That's why we're working with dimensions and with SI units, both. We're solving both at the same time. Okay, we know that AT cubed has to multiply together to leave units of meters per second. Okay? So we have some unknown units here multiplied by units of seconds cubed, which leaves us with meters per second. We want to solve for these unknown units. Well, so to solve this algebraically, we just divide both sides by seconds cubed, and we end up with, they cancel here, we end up with our unknown dimensions, our unknown units, equal to meters per second times 1 over seconds cubed, or meters per seconds to the fourth. Now, does everyone understand how we got to this point so far? Go ahead. Because the equation that we're given to work out tells us that A is multiplied by time cubed, and the units of time are seconds. So we know that we're multiplying some unknown quantity, some unknown set of units times seconds cubed. And then we divide both sides by second cubed to solve for the unknown units, and we find that they are meters per second to the fourth. Now, how would we write meters per seconds to the fourth in just generic dimensions? Meters are units of length, and seconds are units of time. And so that would give us dimensions of length divided by time to the fourth. Meters per second to the fourth in SI units. Now, let's do the same thing to solve for B. At this time, instead of solving for the SI units, we'll solve for the dimensions. Now, B times T is what we know has to end up with what dimensions? What are the dimensions of meters per second? Length divided by time. So here we have B is some unknown dimensions multiplied by a dimension of time. And we know that that must end up being equal to length divided by time. Because that's what we've got to end up with. Meters per second, or length per time. Now, how do we solve this equation for this unknown dimension? We divide both sides by time. Here they cancel. So we end up with our unknown dimension equal to length per time squared. And how do we write length per time squared in SI units? Those become meters per second squared. It's a good thing for y'all to know what the SI units are for the fundamental quantities. What are the fundamental units? I'm giving you a rather overt hint at something that you might want on your standard index card. Okay. Now, any more questions on this one? Okay. Who's got the next one? Anybody? You got another one?
38 is pretty much.
38? All right, everybody finished making notes about all of this? Have you ever noticed that when I erase something off of the board, it leaves a very clean board underneath it that you can still see what I just erased? That tells you that the stuff in these markers is board cleaner. Because that's where the eraser is what leaves the residue behind. This stuff cleans it off as you write with it. In fact, you can stick this under your hat. If you ever have a whiteboard and somebody marks on it with an actual marks-a-lot, the quickest way to get the marks-a-lot off of the whiteboard is to take a black marker, black dry erase marker, and scribble and just go over it with that go over the marks-a-lot ink with that black dry erase marker. It'll take it right off. Do not test that on my whiteboards. Okay, we're looking for 38. Let's see what we're starting with. 3 students derived the following equations in which x refers to distance traveled, v the speed, a the acceleration, t the time, and the subscript 0 means a quantity at time t equals 0. Here are their equations. A x equals v times t squared plus 2at the next student writes x equals v sub naught t plus 1/2 a t squared. And the third student writes x equals v sub naught t plus 2at squared. Which of these three could possibly be correct according to a dimensional check, and why? Now, we're not looking to find out which one is actually a legitimate physics equation, but which of them, just by doing a dimensional analysis, could be true, could be correct, and which ones can we eliminate as wrong just by doing a dimensional analysis? Well, let's start with A. What are the dimensions of x? It's distance, so that will be length. Okay, what are the dimensions of velocity, of speed? Length divided by time, and then it's multiplied by t squared, so that has dimensions of time squared. And then we have 2 times at, 2 times, we don't need to worry about the 2 because that's a unitless number, it's just a coefficient. We're looking at the dimensions. What are the dimensions of acceleration? Okay, and the SI units of acceleration meters per second squared. So the dimensions of acceleration would be length divided by time squared, and then multiplied by time. Okay, how do these cancel? Well, this t cancels with one of these t's, leaving this as length times time. Here, one of these cancels with this one, leaving length per time. Neither of which could possibly equal something that's just length or distance. So we know right away A cannot be correct. Now let's look at this one. The dimensions of x, or distance, are length. What are the dimensions of velocity, speed? Say again? Length divided by time. Times time in the equation, plus, we don't have to worry about the unitless number in front of anything. What are the dimensions of acceleration? Length over time squared, and then it's multiplied by time squared. So when we do this dimensional analysis, we find this time cancels with this time squared cancels with this time squared, and we're left with length added to length, which is legitimate, and the two of them together are equal to length. So B could be correct. Now let's look at C. We have length as our dimensions of x is distance. What are our dimensions of velocity of v naught? Length over time. And then it's multiplied by time. And then it's added to the units of acceleration. Length over time squared. And it's multiplied by units of time squared. So what do we see here? Time cancels time. Time squares cancel time squared. We have length plus length equals length. So this one is possibly correct. I can tell you it's not correct. We'll get to that later when we do equations of motion, kinematics, I think they call it in this book. But from dimensional analysis, this one at least is possibly correct. This one is also possibly correct. But this one cannot be correct. Everybody good on this one? Anybody doesn't? We need to redo it, relook at any of this? I'm sorry.
Like on the question that asks which of these could possibly be right.
Okay. The why is because in order for two things to be added together, they have to have the same units, which means they have to have the same dimensions. Well, okay, let me be real clear about this for a change. Dimensions and units are not the same thing. We're working with the SI units of MKS, meters, kilograms, and seconds. We could, if we go to the next door to the chemistry lab, they're going to work in units of centimeters, grams, and seconds. These are different units. They're both SI units, by the way, but they're different units. But they all have the same dimensions. The dimensions of meters are length. The dimensions of centimeters are also length. Kilograms are dimensions of mass. Grams are dimensions of mass. Seconds are dimensions of time. Okay? In other words, what dimension does that unit specify? Okay? So the units in these two systems of units will be different, but the dimensions will be the same. Okay? Now, in point of fact, when you are working equations, if you're adding this velocity, this dimension of length to this dimension of length, then yes, you absolutely must make certain that they are in the same units as well. Otherwise, you end up adding feet to meters and crashing into Mars. Remember, in this class, we're learning to actually read math for what it means. How is it describing the physical world around us? We're not just looking at the theoretical abstraction of how do you add numbers and how do you solve equations. We're looking at what do these equations actually mean. Now, in this case, just by the dimensions, we have two equations that could possibly be correct. But we know that they can't both be correct. So one of them is still obviously wrong. Or maybe both of them are wrong. But in order for one of them to be correct, it has to be physically meaningful. It has to physically describe the world we live in. So remember that when you're deriving units, you can multiply and divide fundamental units together in order to create new units, new derived units. Okay, but when you're adding two things together, they have to be the same thing, or they don't add, at least not in a physically meaningful way. You can do the arithmetic and say 2 oranges plus 3 apples equals 5 whatevers, but you don't have 5. What do you have 5 of? You have 5 fruit. So before you add them together, you need to change apples to just generic fruit, and then change oranges to generic fruit, and then you can make a meaningful statement. That's the whole crux of this whole thing with dimensions and units, is keeping the equations physically meaningful. And then making sure that they're actually correct is a whole other step. Any more questions? Go. Oh, number 34, okay. Let's look at number 34. Many sailboats are docked at a marina 4.4 kilometers away on the opposite side of a lake. You stare at one of the sailboats because when you are lying flat on the water's edge, you can just barely see its deck, but none of the side of the sailboat. You then go to that sailboat on the other side of the lake and measure that the deck is 1.5 meters above the level of the water. Using figure 116, where h is 1.5 meters, estimate the radius of the earth. This is a good one to work. Let's do this. We have the earth. Now, the land is not very smooth, but the surface of this water is. And it has a radius of curvature that is equal to the radius of the earth. Okay? Now, from right here, you look across and you see just the deck of the ship, but none of the side. Okay? And you know that this height is 1.5 meters. Is that the right number they used? Right. Well, how would we then solve for R? The first thing we would make note of is that this is a right triangle. And where we are laying flat up on the surface, on the edge of the lake, we are at a right angle. We're looking out at a right angle, tangential to the curvature of the earth. Right there, we're at a right angle. We know whatever this angle theta is, we know that the radius plus 1.5 meters is equal to what? The hypotenuse of that right triangle. Now, did it say we measured how far over the lake it is? Yeah, we measured that this distance is 4.4 kilometers. How would we solve for this, for the radius of the Earth in this? What mathematical formula could we use? Say that again? I can't understand.
Oh,
I don't understand what you...
okay, never mind.
No, I'm sorry, I really...
No, I say Pythagoras.
Pythagoras, thank you, yes. Pythagoras. I really am sorry, but yeah, yeah, exactly. We would use Pythagorean's theorem. What does Pythagorean's theorem tell us? A squared plus B squared equals C squared. We know that this length squared, radius of the Earth, plus 1.5 meters squared is equal to 4.4 kilometers squared plus the radius of the Earth squared. Right? Well, how do we square this? You end up with the radius of the Earth squared plus the radius of the Earth. I'm sorry, wait, it would be 2 times the radius of the Earth times 1.5 meters plus 1.5 meters squared, which would give us square meters. And that's equal to 4.4 kilometers squared plus the radius of the Earth squared. Now, trick question. How are we going wrong right now? Just off the top, somebody guess. If no one knows. If you know, tell me where are we going wrong so far? The units are not correct. We can't add kilometers squared. We can add, if the radius of the Earth is in kilometers, these add together to be kilometers, but over here we're adding meters and kilometers. Meters squared and kilometers squared, and that doesn't work. And that would be the easiest way to do it. Just change this to 4,400 meters. So, (4,400) squared meters squared. But now that will give us the radius of the Earth in meters instead of kilometers. Everybody see that? Yeah, the radius, we can estimate the radius of the Earth in meters and then change it to kilometers if we want to. That's an easy enough thing to do, just divide by 1,000. But yeah, as long as we make sure that we're working with all the same units. We can't solve this equation and then say So it's, and then say that works out to so many kilometers of Earth radius. We have to remember that we're getting the radius of the Earth in meters, not kilometers. Now, what does everyone see when they look at this equation? How would we go about solving this? Yeah, we definitely want to simplify it first, because if we just start solving it by the bigger hammer theorem, by brute force, we're looking at a quadratic equation that we have to find the roots for. But we have radius of the Earth squared on both sides of the equation. So and how do we cancel them? You have to do the same. Whatever you do to one side of the equation, you have to do to the other. That's fundamental rule of algebra. Since if we subtract the radius of the Earth squared from both sides, then these go away. And we're left with 2 times the radius of the Earth times 1.5 meters plus, what's 1.5 squared? Plus 2.25 square meters is equal to, now we got to square 4,400, and that's 19,360,000. So we're going to write going to keep this. I'm going to write 19.36 times 10 to the 6 meters squared. And that's it. The radius of the Earth has been eliminated over here. Now we're looking to reduce this down to the radius of the Earth. So let's subtract 2.25 meters squared from both sides. And we end up with just 2 times the radius of the Earth times 1.5 meters is equal to now it messes up that nice scientific notation, so I'm going to go back to 19,359,997.75 meters squared. Everybody noticing over here, we're multiplying 1.5 meters, not meters squared. How is that equal to something that is in meters squared? Exactly, because the radius of the Earth is also in meters. So this is, by dimensional analysis, length times length equals length squared. Everybody see this? I'm just trying to point this out so you can see how to stay on track as you work through some of these more involved problems. Now we divide both sides by 2. And we have the radius of the Earth times 1.5 meters is equal to 9,679,000 998.875 meters squared. Now, I'm keeping a whole bunch of extra digits here, aren't I? I want y'all to think about this, because I'm actually solving this equation arithmetically. How meaningful are all of these extra digits? Say again? Yeah, the fact is that this is way, way beyond the precision of our original estimation. We should be looking at 2 digits. And then our final answer, we're going to remember that. But at this point, we just divide both sides by 1.5 meters. And we end up with the radius of the Earth. When we divide this side by 1.5 meters, this meter cancels one of those meters, and we end up with the radius of the Earth to 2 significant digits. It comes out to 6.4, 1, 2, 3, 4, 5, 6. And you know what? Before I do that, I'm going to divide by 1,000 to go back to kilometers. And we end up with 6,453 kilometers, which to 2 significant digits is 6.5 kilometers. I'm sorry, not 6.5 kilometers. Well, that would have been a foolish mistake. 6.5 times 10 to the 3 kilometers. Is that the right number? Yeah. Or 6,500 kilometers. Okay. Now, do we see how this is done? And it looks like we have just gotten to the end of this period. Do we have any more questions? Well, if any of you have any questions, I have my office hours today, and I'll probably be around for a while after those, so come around if you need.